Good afternoon, ladies and gentlemen. So let me start this seminar, and it's my great pleasure, and I really would like to thank František for coming to introduce you our today's speaker, who is Professor František Švec from Faculty of Pharmacy, Charles University in Hradec Králové, or Prague, let's say. And so before the lecture starts, let me briefly introduce our today's speaker. So František Švec did his study and PhD at the Institute of Chemical Technology in Prague, and then he also started to work there. More importantly, in 1992, he moved to USA. At first, it was Cornell University in New York, and then University of California at Berkeley in California. From 2005 to 2014, he was facility director of Lawrence Berkeley National Laboratory Institution at the Molecular Foundry, and then he also worked at China, and currently he is working in Hradec Králové. So the major scientific achievement is development of polymer particles for several different applications, but the more importantly, it's invention and pioneering of novel monolithic porous polymers, which were introduced in 1992. His research resulted in more than 500 publications with 26,000 of citations and impressive number of H-index of 93. František is also a member of several different chemical societies, and he worked as editor-in-chief in Journal of Separation Science and Separation Science Plus journals in Wiley. And I have to say that during the 20 years of working him as editor-in-chief, he really moved the Journal of Separation Science up, really. It was nice. And his work was awarded by several or numerous different awards. I would like to highlight 3 of them. Golay Award in 2005, and also AJP Martin Medal in 2013. So far, only 3 people from Czech Republic or Czechoslovakia were awarded by this award. And more recently, this year, František received a Neuron Award for a lifelong contribution to the science. So with that, I will move to our Director of Department, Petr Táborský.
Thank you very much. So welcome, Professor Švec. So on this occasion, I would like to present to you, speaking about medals, so I would like to present you bronze medal of Masaryk University. Congratulations and thank you for coming.
Wow, looks better now. Actually, if you are wondering about the title of my talk, you know, by education I am a polymer chemist, and I switched to analytical chemistry in my late years, and my impression is that a combination of 2 different sciences or fields, if you like, is a fertile soil for doing things that typically in the single field are less probable. So this is why I am going to tell you something about the porous materials, but you will see that it has a very close relation to the analytical chemistry. So what are we going to talk about today? First of all, let's define porosity, because this is what are we going to talk about all the time. I will show you how the porosity in the polymer-based materials come to the life, why and how to make them. I will also show you why we need to work with porous materials and what are the problems of using porous materials, because we have to deal with diffusion, and we will define everything. Then I will show you how the monoliths have been born and what was the evolution to the today's state of the art in the area of monolith. I will show you how to make them in different formats. I will show you the less common ways how we can modify the structure as well as the chemistry. Depending on time, I started late. We will see what we can do with the gold era of monolithic materials. And at the end, I'll show you some unbelievable things that monolith can do, and you will not believe your eyes. So, the International Union of Pure and Applied Chemistry defines porosity in 3 different levels. The smallest pores, smaller than 2 nanometers, are called micropores. Between 2 and 50 nanometers are called mesopores, and larger than 50 nanometers are called macropores. I would prefer nanopores rather than micropores, but IUPAC didn't hear to me. And then some people try to use the word megapores with pores over 800 nanometers, which I don't think is something which will go through IUPAC as well. So this is the definitions. Why we need the macroporous materials? Let's start with particles, because particles were first in this field, and we will see right away. So first of all, the issue is that these macroporous particles were used for ion exchangers. And the reason why they were needed in this field is that the typical materials based on styrene divinyl benzene didn't work so well, and there were some problems with swelling during applications. The mechanical strength was limited, and also the mass transfer was relatively slow, and therefore we needed to develop macroporous polymer particles. The first macroporous particles were prepared in the mid-1950s. How come? The issue is very simple. You probably know what was the Project Manhattan. We had a movie recently. And during that project, the scientists were asking for very pure lanthanides for their work. And these lanthanides were separated using ion exchange chromatography in Ames in Iowa. The columns, big columns, are still there. If you go there, you can see them in the museum, University Museum. And they really separated them. No one knew, simply because the ion exchangers used at the time were confidential or actually secret. They were based on 2% divinyl benzene cross-linked porous, non-porous styrene divinyl benzene particles. And the public got the information only in 1948. But almost immediately, the energy field was very much interested because that was the way how to demineralize water for power stations. And it turned out to be a very good method for that. And therefore, ion exchangers were booming extremely quickly. But because of these problems I showed you in the previous slide, the problem was that they didn't work extremely well for those applications large scale. So these three gentlemen, Irving Abrams, came with methods how to make these particles porous. Abrams, whom I met one time in the early 1990s, used polymer as the porogen. Porogen is a part of the polymerization mixture that occurs to get the desired porosity. The second one was Mike's, essentially the same year, using porogenic solvents. So, for example, for styrene divinyl benzene, he used toluene because it dissolves well the polystyrene type of molecules. And the last one, a couple of years later, Erich Meitzner used non-solvents as porogens, precipitants, if you like. And this gave the producers a very nice tool to create materials. The first one, the Abrams' technology, was not very well designed for large production, but I liked it. It was a very intelligent solution to the problem. I have no time to go into details. And the Meitzner stuff was that has been used and is still used for the production of macroporous styrene divinyl benzene ion exchangers. The funny thing is, as I said, these methods were described in patents, and Meitzner et al., working for for Roman Haas, was submitting a patent application, and this patent application has been treated by the United States Patent Office for 18 years. Imagine that. Eventually, Roman Haas received the patent. Meanwhile, all different companies were producing their porous particles using exactly Meitzner's technology. So the lawyers of Roman Haas sit down and wrote a letter to all these companies telling them, hey guys, we really appreciate that you are making particles using our patent, but as you can imagine, we will ask you to pay the royalties. And really, 99% of all these companies started to pay the royalties, except for one. And the one company started to sue Roman Haas to tell the judge that this patent is no patent, no nothing new, etc. But Roman Haas at the same time submitted their problem to the same judge and told him, hey, judge, they are not paying the royalties and infringing our patent. So there was all of the sudden treatment of these two things together. I happened to be one of the expert witnesses. It was very funny. 3 weeks I spent during this trial. The result was very funny because due to some stupid problems, very unbelievable, missing some paperwork, the judge decided that it's okay. The one company doesn't need to pay any royalties, and the patent is still valid. Anyhow, so that's the life. So the typical particles, spherical particles, porous particles in our case, are prepared by a suspension polymerization. As you can see, it's very simple in the lab scale, obviously. And we need to have two things. One thing is the aqueous phase that is right here, which is essentially water and suspension stabilizer. And we need to have the polymerization mixture that consists of a number of compounds. I will show you some later on. Then you start mixing, you create these droplets of the polymerization mixture that are stabilized by the stabilizer. And then once you heat up all the system, these particles polymerize, you are creating macroporous polymer, and eventually once the polymerization is completed, you remove the particles by filtration, you wash them and you have them. And if you want to make ion exchangers, you need to modify them, which is typically something that is typical polymer chemistry. Interestingly enough, the Czech Republic, or Czechoslovakia at that time, was very much ahead of the rest of the world in the definitions of the preparation of macroporous particles, what are the rules, what can be done, and so on. And all this has been essentially summarized in this review article, 100 pages, where the people from Pardubice and from the Institute of Macromolecular Chemistry of Academy of Sciences in Prague, together with Heitz, who essentially cared about the English, actually German in this case, prepared this large review article, which is kind of Bible of macroporous polymers even today. You know, unfortunately, Karel Dušek passed away about 2 years ago. Anyhow, so what are the typical applications of macroporous polymer particles today? Well, I already said that. The modern ion exchangers, which is large commodity in the nuclear power station, all the power station in reality, in the other applications where you need to have demineralized water, they can serve as catalyst carriers, metals, enzymes, acids, bases, you name it. You know, they can be used as adsorbents for water treatment in biotechnology, bioprocessing, for the downstream processing, tissue engineering, sample prep, and chromatographic applications. They are mostly used in packed columns because that's the easiest way how to use these particles. Let's have a look at such a packed column. So this is an example how this packed column looks like. We have these porous particles right here, and the liquids that we are pumping through this column go through the interstitial spaces between the particles. Typically, the rule is that essentially the size of these intraparticle voids is about 20% of the size of the particle itself. So if you have 10 micron particles, this is about 2 micrometer space. Now, I spoke already a little bit about the mass transfer. So let's have a look what's happening. We have porous particles, and we have the flow between these particles. However, the flow is going around the surface of these particles. The surface is typically very small. I mean, we are in the best scenario speaking about single square meters per gram, which is not good for any separations, whatever they are. And what we need is to use the porosity, the porous structure of these particles. So just to simplify everything, let's make this single pore in this single particle. And this pore is connected by, this entrance is connected through the pores to the interactive site of the macroporous particles. Now, we have all those compounds that we need to separate, manipulate, modify, etc. in this flow. So we need to get them from this flow to this interactive site. This pore contains the same liquid, but the liquid here doesn't move because it is stagnant, because there is no way how it can move. So now we need to make sure that from the outside, our compounds go through this pore to the interactive site, they interact, and then happens something, whatever. Once the interaction is completed, the products or whatever have to go out again. Now, what is the mechanism? The mechanism is diffusion. And so this is very interesting. Soraj, this is so what we need is to think about what we can do with this issue. So let's go back and look what Adolf Fick told us about diffusion already 150 years ago. He said that the change in concentration with time is related to the difference in concentration related to the distance squared. So this is the second law. Interestingly enough, we can think what we can change in this diffusion to accelerate the diffusion. Because obviously, if we want to make fast separations, we need to make sure that it goes in and out quickly. Well, so what we can do? Let's look, for example, on the diffusion coefficient. Here we have two guys who contributed. It was Stokes who came up with the idea of flow around solid bodies, and Albert Einstein, in his PhD studies, came up with this simple equation that tells us what is this diffusion coefficient all about. So it consists of Kb, which is Boltzmann constant. There is nothing we can do. It's a constant temperature. This is here. Here we have viscosity of the liquid in the diffusion is occurring, and size of the moving, diffusing items, molecules, whatever. Okay? Interestingly enough, I thought that these two gentlemen could see each other because they overlapped by about 23 years, but I don't think they have really met, but they could. Now, this is an interesting equation because what we can change if we want to really affect diffusion. Temperature, well, most often we can go to, I don't know, 90, 80 degrees C, which is not too much. Viscosity is given by the mobile phase that flows between the particles, and the size of the separated or manipulated molecules is given. We cannot change it at all. Right? So there is not much we can change, and therefore diffusion coefficient is not any way to accelerate diffusion. So what can be done? Let's look at the distance. Okay? Now, the easiest way to avoid the effect of distance is to use non-porous particles. Actually, this is nothing new because this iChrome company in the United States makes columns that are non-porous. The packing is non-porous. The column size is 3 centimeters, typical size, particle size 1.5 micrometers, very tiny particles. Therefore, the column must be short because we will see why. And the issue is that the outside surface area is less than 3 square meters per gram. So the loading capacity of this column is very limited because there is no space to accommodate all the compounds we want to separate, for example. So this is not the right way to go. What else? We can use smaller particles. If this is the particle which we call large, with a diameter RL, like large. So if we make the particle smaller, diameter smaller, S, then obviously the distance that the individual molecules have to travel is shorter. We cannot change diffusion. We can change the distance. So if the distance is shorter, the diffusion is shorter in time, and therefore we can accelerate all the process. Now, this is interesting because this is an idea the Agilent Technologies company came up with columns they introduced in 2003 with the sub 2 micrometer small particles. And at the beginning, they used only short columns. This one is longer, this is new one. 1 year later, Waters company came up with a system that enabled to use these longer columns, because this system could work with much higher pressures. You know, this is actually named by UPLC, Ultra Performance Liquid Chromatography. This trade name has been introduced by Waters in 2004, and you can see that here we can go to pressures, back pressures in the column up to about 100 megapascal, or in America it is 15,000 psi. Now, the problem, I'm showing that it may happen, is shown here. These two gentlemen, Joseph Kozeny from Austria and Philip Carmen from Scotland, developed an equation that tells that the pressure drop across the column depends on viscosity of the liquid, length of the column, and flow rate, divided by square of the column diameter, and divided by the square of the particle diameter. So the smaller the particles, the larger the back pressure or the pressure drop in the system. So here we have an issue. And this is why Waters came up with systems that could work at much higher pressures than the previous versions of the HPLC systems that were typically good for about 400 to 600 bar or 60 megapascal. However, there is nothing like free lunch. And this man, Ken Brockhaven, demonstrated used this equation to demonstrate that there is a problem with friction heat. You know, the pressure we are using is energy. Sorry. And this energy has to be somehow dissipated. And the energy is changing to the change in the temperature inside. And well, changing temperature during the run means that we have system that is not homogeneous. You know? We have to get rid of the heat, and this is a problem. So decreasing the size of the particles has also this negative issue that has to be dealt with. You know, so we cannot go too far down simply because we would run into trouble of the friction heat. So this won't work, smaller particles to a certain extent. So why don't we use particles that have the same size, but in the middle they are not porous, okay? So now the length for diffusion is shorter than here, obviously, and therefore the diffusion is shorter as well. Well, there are some small problems because the volume of the particle, of the porous part of the particle, is smaller than here. Therefore, the loading capacity is smaller. And, well, we also have smaller surface area, obviously. So, smaller loading capacity. So what to do? Actually, Kinetics, smart company in South California, came up with the idea to make combination of these both smaller particles and the core shell technology. And they are selling these columns with the size of 1.3 micrometers particles like this. Well, it sells, it works, but it works only for small molecules. Or I would put it this way, I didn't find any application for large molecules. What else? We have the monolith, and we are coming to the point that I am very much fan of. Well, monolith, it's nothing new in the world. As you can, we have monolith of castle. This is, the monolith is from Greek, mono meaning single, and litho meaning stone. So single stone, obviously. But let's go back a little bit, okay? Once upon a time, we may speak about very ancient monomers. So Arthur C. Clarke wrote a book, 2001, A Space Odyssey. Stanley Kubrick made a movie based on this book. And the story is very simple. There was a group of apes, Homo erectus, you know, that was living in this cave. And other groups of these apes were living elsewhere. But these apes were lucky because this monolith was just in front of their cave. On one day, all of a sudden, this monolith started to glow. Okay, and the glow, remember, the glow was primarily affecting the brains of these Homo erectuses, and they became smart. And this was good because simply they were smarter than all the other apes, and they were fighting with them and enlarging their area of work and so on and so forth. So this is something that happened about 1.6 million years ago, long time ago. Interestingly enough, though, what is this? This is a monolith that has been found in Utah, in one of the deserts there. Well, I don't know, obviously, no one knows whether the history repeats itself and this monolith should help to enlarge the brain capacity or something like that of the present mankind. Then I am wondering, if this is the case, why this monolith is located in, I don't know, in Utah, in desert, and not, let's say, on the Red Square. But this is not my business. Anyhow, have a look at the definition. Monolith, by definition that I found in Google, you say monolith, 71 million hits right away. Okay. Here we go. If we go 2 hits per second, we will need about 2 years to see them all. The problem, though, is anyhow that this definition is completely useless. Geological feature consisting single massive stone on so. So it is something like this, you know, the half dome in California, or this stone of pregnant woman in Asia. No one knows how it happens to be there because it's not manipulable even with today's mechanisms. Or this lion rock in Sri Lanka, which is very nice monolith, I like it. But the one I like most is this one, the so-called Uluru in the Australian native people, or Ayers Rock using the English. It's 350 meters tall and about 10 kilometers around if you want to walk around. What is the general problem of all these monoliths? They are too big to fit in any lab. You know? So this is not the way to go. So this is why I had to develop my own definition that a monolith is a porous solid consisting of a single piece of inorganic material or organic polymer produced by polymerization reaction within the confines of defined container or on a surface of a solid support. Okay? So the early approaches to monolithic materials go back to 1960s. And interestingly enough, again, the first paper on this topic was written in the Institute of Macromolecular Chemistry. Mirek Kubin was the one who was working with materials that were used for the soft contact lenses. That's what Wichterle developed in UMH, and this is why they used this material for their experiment. It didn't work extremely well. I have no time to go in details. Then 7 years later, these two groups, one in Germany, one in at the east coast of the United States, came up with polyurethane foams with open pores. They looked like the monolith we are using today, or are similar, but the chemistry, polyurethane, is not good chemistry for any separations. So this didn't work. The modern approaches started only in 1989. First, in the Institute of Macromolecular Chemistry, we developed these discs. You know, the monolith is inside. The colorful rings around is not just to make them colorful, but it is indicating what type of chemistry is inside. So you can, by color, define the chemistry. Then in early 1990s, with Jean Frichet, when I was already at Cornell, we came up with the continuous rods columns, because simply the chromatographic community didn't like the discs. They were not used to use any discs. They are using columns. So we said, well, if the chromatographic community wants columns, let's make them. You know, we didn't know whether or not it is possible to make them, but eventually it turned out it was possible. So we were very successful with this. And this is the first paper we published in 1992. It has well over 1,000 citations currently. And the last contribution in this field came from Nobuo Tanaka from Kyoto, who came up with the silica type of monolithic columns. Just for curiosity, I was sharing apartment with Tanaka for some time when I was at Cornell. So we spoke together all the time about everything, obviously. We cooked for each other. And Tanaka told me, please, never say anyone that I cooked. Japanese men do not cook. Okay? So, please. Anyhow, so Tanaka came up with these monolithic columns. This is one of the columns that is now produced by Merck. This is the inside structure. We will see later on a little bit more. This is the box they are selling these columns in. Look at this. It's rather dull. You know, there are nothing, just letters. Okay, so let's go to the polymer-based monoliths that are closer to my like. And first of all, again, typical Googling, only 1,700,000 hits. It's much faster. It's only 20 days. I didn't do that. And you can see a number of very interesting reasons why the polymer-based monoliths are good for taking them into consideration. So first of all, we don't need to pack columns as with the particles. Then, obviously, we prepare these columns in situ. We have liquid polymerization mixture, I showed you already at the very beginning. We fill the tube, and the polymerization may start. We can vary chemistries and formats very easily. Chemistries, because there is a number of monomers available not only on the market, but also we can prepare them by ourselves. Formats, you will see a couple of them right away. These monolithic materials enable fast flow rates and low back pressure, which is important. Facilitate rapid mass transfer via convections as opposed to diffusion we discussed at the beginning. And it also allows high-speed separations of large molecules. So, this is the commercial polymer-based monolithic column that is made by Thermoscientific. This is the column. This is the internal structure. This is how does it look like if you remove it from this column. And look at the box. You know, it's colorful. It's much nicer. You know, and it's my work. Anyhow, so the internal structure of the polymer-based monoliths looks like this. We call these globules, or this is a globular structure, but as always, we are way behind the Mother Nature, because I found that Mother Nature created this structure some time ago. You probably do not know what this could be, but I will show you. It's a fish poop which is about 12,000 years old, completely mineralized, and it has been published recently in PNAS. Now let's go a little bit to the polymerization technique used for preparation of both particles as well as mostly for the monolith. So this is typically free radical polymerization. It has been initiated to create the free radicals and achieve the polymerization. And this can be achieved by heating the system using redox systems, radiate them by UV light, electrons, gamma rays, you name it. Or we can even use stable free radicals, which are well-known compounds in the polymer chemistry. So what we did, we used the same polymerization mixture consisting of glyceryl methacrylate and ethylene dimethacrylate. We prepared particles and we prepared the monolith, and then we measured the pore size distribution. To our big surprise, we found that they were not equal, although the polymerization mixture was the same for both these applications. So we were really scratching our heads, asking how come that the same polymerization mixture gives two different pore size distributions. And, well, we were thinking how to explain this. And I think the reason can be seen in this movie that has been... movie doesn't work. Why? It seems to be important to show. Okay, forget it. It doesn't work. Anyhow, I will tell you. If you see the movie, you will see that after some time, this is the polymerization mixture. This is behind a window. The sun is shining on this mixture, and the polymerization starts because the UV light from sun is creating the free radicals. And as the polymerization starts, you see some kind of foggy thing that is created within this liquid. The foggy thing is the polymer that is heavier, denser than the polymerization mixture because the molecules are closer to each other. And this starts to sediment, and the monolith is created from the bottom up. So this does not have any specific mixing, any changes in rotation, nothing. So simple precipitation and sedimentation. So after thinking even more about it, we decided that the reason for this big difference is the effect in suspension polymerization. Because if you mix, in this case, we can see the sedimentation. If you mix the particles, there is nothing what can sediment because they are moving all the possible ways, And then on the top of that, the particles, the droplets are decreasing in size because, as I said, as the polymerization mixture polymerizes, the distances between the molecules are shorter, and therefore the droplet is decreasing in size. in volume, and also we have the interfacial tension at the interface, water aqueous phase, and the polymerization mixture phase. So this is what compresses the particles during the polymerization, and therefore we have small pore size. If we want to prepare a monolithic polymer in a column, we can do it very easily. We use the polymerization mixture. We fill the mold, which is a column. The polymerization mixture consists of vinyl monomer, which can be styrene, butyl methacrylate. We have to use a cross-linker, which is divinyl benzene ethylene dimethacrylate. We can use functional monomers like chloromethylstyrene, we will see, glycidyl methacrylate. We have to use porogenic solvent, which can be cyclohexanol, dodecanol, toluene, tetrahydrofurane, and we have to add an initiator. Once we have all this, we close the column, we heat it up, and then we pump a solvent to remove the porogenic solvents from the pores, and we can use it right away. When we use it for the separation of proteins, you can see that at very small back pressure, we can separate 5 proteins in about 18 seconds. This was in 1996. At that time, it was really very fast separation. We can even use this material for size exclusion chromatography, shown here. Again, typical size exclusion chromatography that is used to define molecular mass of synthetic polymers. It takes hours. Here we can do it in about 7 minutes, and as you see, the calibration curve is very nicely straight. So the question is, why all of a sudden we have such a slow separation or slow problems in the packed columns? Because we are using diffusion for the mass transfer, while in the monolithic column, all the mobile phase, all the liquids flow through the pores as opposed to the around the particles, and therefore we are using fast convection, which brings the individual molecules to be separated close to the interacting site by flow, and we can control the flow easily. Well, small monomer, small monolithic columns, same problem. You fill the capillary and so on, which is exactly the same as we used previously. In this case, we can even use UV initiated polymerization and get again the desired separation. As you see here, we can demonstrate very well the porous structure. This is 100 micrometer capillary, and we can use it for separation. Here is a less usual separation of proteins again in less than 1 minute, where we used a very unusual gradient. At the injection point, we increase the concentration or percentage of the good solvent immediately from 10 to 50%, and we receive very nice separation with symmetric peaks in about 0.8 minutes. Problem is, if you want to make large monolith, because the polymerization reaction is exothermic, and therefore we have to deal with the heat of polymerization. So Eric Peters essentially prepared this experiment with 3 different thermocouples measuring temperature at 3 different locations. And if you look at what's happening during this large-scale preparation of the monolith, you see that with the methacrylates, after about less than 1 hour, we see the increase in temperature in the middle from the nominal 55 degrees C to about 110 degrees C, which is a big difference. The same or similar you can see with the styrene divinyl benzene. Why we don't like this? Because we know that temperature is one of the factors that we can vary to change porous properties. So if you have different temperature inside and outside of the monolith, you have a gradient of porosity, which is not desirable for the applications. And there is no way to distribute or remove the heat from the middle easily. So this is an issue. How to solve it? This gentleman, Aleš Podgornik from Slovenia, came up with a very interesting solution to that problem. Why to make a big monolith in a single piece when we could do it in several pieces that we put together in this way? And all of a sudden he had a big monolith easily without any pore size distribution. The company, Bia Separations, is using this technology for their production. They have tubes that are up to 40 liters large, which is really quite large, starting from 1 milliliter, 8, and so on and so forth. And the flow rates are very high, 10 liters per minute, but it doesn't matter. This is this technology I showed you. And here is how they use it. If you have these tubes, you cannot use it in the tangential way, meaning pumping on the top and getting the separation at the bottom. So they started to work and use the radial type of flow. And essentially, this has a couple of advantages. One advantage is that the thickness of the layer you are pumping through is much shorter than this one. Right? So the back pressure in the system is much lower, and therefore it's much easier manageable. And the industry doesn't like high pressures. Industry likes pressures that are reasonable. So the Bia company, that is part of the Sartorius, makes these large columns I told you about in this format, from small to very large, which is good. Just for telling you what can be done. The polymerization techniques are here. Again, I showed you already the free radical polymerization, but there are some others described in the literature: metathesis, polymerization, atom transfer, free radical polymerization, anionic, which is outlandish, polycondensation, click reaction. I don't think I have much time to go to all of them, so let's focus on a couple of examples of polycondensation that has been done in Sweden by Knut Irgum. They use very simple reaction, as you can see, and they received monolithic materials that has structure similar to what we are doing with our polymerization. Here is another one which is a little bit more complex. This came from China, and as you see, the structure of this is similar to that of the silica-based monolith. Okay, and this is the last one, the click reaction that has been developed by Hanfa Zhou in Dalian in China. And they are using click reaction, which is reaction of a thiols with triple bonds of, let's say in this case, octadiene. And again, they using different thiols, they can change the structure of these monoliths and use them for different applications. We can control the porous properties as well, simply because, as I said, the separation using silica-based monolith is a little bit different, simply because the structure is different. As you see, Nobuo Tanaka separated 5 alkyl benzenes in about 30 plus seconds in 1996 and received about 100,000 plates per meter. If we used a similar approach, made our monolith and tried to use this for separation of alkyl benzenes, we needed about, in the best scenario, 15 minutes, in the worst scenario, about 30, which is completely useless, and the separation efficiency, 13,000 plates, is fun, it's completely useless. So what to do? Well, the reason why it didn't work probably is that our polymer monolith has only small surface area, which is the surface area of these individual globules. While the silica monolith, all these building blocks are porous by itself, and therefore the surface area is in about 300 square meters per gram. So what to do? Well, we can control porous properties using polymerization techniques. Well, this is one option, using temperature, percentage of crosslinker, porogens, polymerization time, chemistry of the monomers. But I'm going to speak about one which is really a polymer chemistry, and it is called hypercrosslinking. And it has been developed by Vadim Davankov in the late 1960s. Vadim Davankov passed away early this year, and he published or patented this in the United States, and then used it for the hypercrosslinking of linear high molecular weight polystyrene, but has never been used for monolith. So we try to do so. The process is very simple. It's solvation of polystyrene-based monolith in a good solvent like dichloroethane, and initiation of rapid cross-linking reaction, which is in this case Friedel-Kaufz. It has been developed by here present Jiří Urban, and essentially this research is continuing in this place even now. A very simple process. You prepare copolymer of the 3 monomers using toluene dodecanol porogens, azobis isobutyronitrile initiator, and after the polymerization you are getting a monolith that looks like this. Divinylbenzene polymerizes faster, simply because, very simplified, it has 2 different double bonds, therefore twice as many as the other 2 monomers. Therefore, it disappears from the system. Close to the end of polymerization, these 2 monomers prevail in the polymerization mixture and create, in fact, chains that are not cross-linked at all. So what we can do, we essentially swell this system with a good solvent, dichloroethane, and once when the system is swollen, we cross-link these swollen chains using Friedel-Kaufz reaction, and we are getting much more smaller pores, which has big advantage because it immediately increasing the amount of small pores, like in this area. This is a logarithmic scale, so don't worry too much. As you see, this is the original monolith, this is the hypercross-linked counterpart, and we see that the quantity of these pores is increased quite significantly. From the beginning, we have about, depending on the vinyl benzyl chloride present in the system, about, I don't know, about 10 square meters per gram. After the hypercross-linking, we can go up to 600 square meters per gram, which is significantly larger. This is one of the applications, separation of alkyl benzenes. We have seen that with the Nobuo Tanaka's publication. Now we are already having 73,000 plates per meter for benzene, which is this second peak, and we are approaching what we want. If we do not like to optimize system that consists 3 monomers, we can perhaps think about removing the chloromethylstyrene. But then we don't have the reactive system there. So we have to use external crosslinker. And these external crosslinkers are shown here. You know, again, these are molecules that contain 2 chloromethyl functionalities, like here and here. And it seems to work very well because using this approach and manipulating time of polymerization, we can again obtain monolithic material with well over 800 square meters per gram, with a large fraction of the pores in the area of micropores, and the others are the meso and macropores. I think this is probably time to call it. We have to go through this. Okay, so in conclusion, the monoliths are now a common part of the porous polymer family. They can be prepared in different sizes and formats. I showed you a couple, the columns and capillaries. There are some new approaches that has been developed for control of porous properties, including hypercross-linking. And the range of applications is continuously increasing. And next time, I may be interested in come and tell you about some other applications. But, you know, I have to express my special thanks to people who contributed to all the experiments I showed you, and they are shown here. But you may wonder, why state of California? And I'll show you why. Because if you go from, let's say, San Francisco down to Arizona, you got to go this way, okay? Here is the Mojave Desert, okay? So there is absolutely nothing, almost nothing. And you come to this place that is shown by the asterisk, and you have an exit from the freeway. Well, interestingly enough, there is this type of area. You know, this is a company that makes concrete, nothing special, okay? But we can show you that the monolith can be used for energy storage. And this is this one, the Tehachapi energy storage project that includes about 8 megawatt or 32 megawatt hours of lithium battery-based grid energy. And it's called Monolith Substation. This amount of energy is enough to provide about 2,000 homes for 4 hours. It's not too much. But the price of this substation is about $50 million. And the substation includes about 600,000 lithium-ion batteries that are located in these banks and cells. And obviously, it demonstrates that this storage of energy is not a cheap stuff. And finally, again, Hollywood, I started with. And we had this movie produced in 1956. And this is all I am going to tell you about the monolith. Thank you for your attention.